On the last lecture, we finished on the following identity, something like this: n choose k plus m plus 1, k plus 1, etc., etc. n plus m choose k plus m is equal to n plus m plus 1 choose k plus m plus 1 minus n choose k plus 1. Yeah.
We have some kind of time.
Yeah, so you can. I just sent to all of you a link to the Google Drive folder, when you can have like 10 or 15 books on combinatorics and graphs. And so if you want to ask me about different lectures, just write in a mail or just ask me in Telegram, and I will send you a link to this. For example, for combinatorial identity, I need that one book. For the graphs, maybe I need other book. But so this one, I think covered in book by Gennadievich, Introduction to Combinatorics. I need to just check it if I'm right. Okay, thank you. Youngman, Introduction to Combinatorics. Yes, this is right. So I think you can find all the combinatorial identities that we discussing in this textbook. But if you can't find it, just ask me and help you. Pahit, what do you mean by choose any order of numbers? Could you be more specifically? Because I maybe can you provide an example? Okay, so I want to use similar formula to this one. So I will start with k choose k, add k plus 1 choose k, etc. And the last one will be k plus m choose k. And so this is equal to k plus m plus 1 choose k plus 1. So what was the difference between these two formulas? If I can illustrate it by writing a Pascal triangle. So if I look at the upper one, I just take some element and then take the elements line on the one diagonal. And the second one, for example, I take k equal to to 2, then I want to take 2 choose 2 is here, then I want to go 3 choose 2, 4 choose 2, 5 choose 2, and so on. So I take the symmetrical diagonal and from the start. So I take first element will be lying on the border of this triangle, and then I go to the this diagonal. And so the answer will be, we'll write the following row. Here, 1, 7, 21, 35, 35, 21, 7, 1. And so the sum of these elements will be, if I'm correct, this guy. So 1 plus 3 plus 6 plus 10 plus 15 will be 35. Do you understand this formula? No? How can we prove that if I summarize all these red elements, then I get this green element? Okay, for your question, I don't think there are, so for some elements like this one, so if you want to summarize a diagonal, then I can write an explicit formula like this one, because I'm using the property of the Pascal triangle, and just adding numbers, I can just get rid of the sum. But if I, for example, take choose all the middle elements as you asked, for example, this one, that I don't think there will be explicit formula for arbitrary parts of the binomial coefficients, because I cannot use the Pascal main Pascal triangle property here. But sometimes I can. So we just on the previous lecture we calculated the sum of all elements in the row, or for example the sum of all even elements in this row. So some of this we can have formula, but for the arbitrary parts of arbitrary row, I don't think we can have an explicit formula. Okay, so how do we get 35 here? Can someone explain me?
Every element, for example, if you choose 15 and if you look at the next element,
Yeah.
20, this will be sum of the previous one.
Yes. Yeah, so we can just start from the beginning. So first of all, we move this one to this element. This is the same. And then we just use the main property of the Pascal triangle. So the sum of these two elements will be this element. Sum of these two elements will be 10. Sum of these two elements will be 20. And sum of this element is 35. So if we want to summarize all these elements, all we need to do is just take the element that is right and down next to the last element of the sum. So I can just, so if I want to write the proof, I just first mentioned that k choose k is the same as k plus 1 choose k plus 1, as I'm doing here. And then if I use the same identity that we were using before, so k plus 1 choose k plus 1 plus k plus 1 choose k is k plus 1, k plus 2 choose k plus 1. If I add this to the k plus 2 choose k, that I will have k plus 3 choose k plus 2, and so on. And then I will have k plus m. Sorry? Здесь? Okay. So the last one will be k plus m choose k plus 1 plus k plus m choose k. And then this will be equal to k plus m plus 1 choose k plus 1. Okay? And I want to show you that some combinatorial identities can be used to achieve some results in number theory. So for example, from this identity, we can calculate the sum of powers. Okay. Now I want to suppose, so I'm sure that you know what is the sum of the first n natural numbers are, but maybe you don't familiar with the sum of squares, sum of cubes, and so on. I want to find the explicit formula for these sums. So for example, if you consider the first one, we can see this just into Pascal triangle, because if I want to calculate the sum of 1 to 1 plus 2 plus 3 and so on, I just want to calculate the sum of this diagonal, because I can rewrite this as 1 choose 1 plus 2 choose 1 plus etc. plus n choose 1. And so was the formula on the right board. I need to write n plus 1 choose 2. Yes? So here k is equal to 1 and n is equal to m. And so n plus 1 choose 2. By the formula, I need to divide n plus 1 factorial to the 2 factorial time n minus 1 factorial. And so this is nothing but n plus 1 over 2. And this is just the formula for the sum of the first natural numbers. Okay? So what if I want to calculate the sum of the squares? Here in the Pascal triangle, I don't have squares, but I have some similar numbers to squares. If I look at the next diagonal, So this one. So what if I look at the of the formula of k choose 2? K choose 2 is k plus 1, no, k minus 1 over 2, and this is k squared minus k over 2. So I have k squared, which I need, minus some linear k and divided by 2. So if I look at the sum of binomial coefficients, 2 choose 2 plus 3 choose 2 plus etc. plus n choose 2, then I can rewrite this as 1 divided by 2 times 2 squared minus 2 plus 3 squared minus 3 plus 4 squared minus 4, and so on, n squared minus n. Okay? So here I have this sum that I want to find. 2 squared, 3 squared, 4 squared, n squared. So first remark that I can add to this sum 1 squared minus 1 because it is 0. So I can just add it here. And so this formula from the left-hand side is nothing but sum of the squares minus sum of the first n natural numbers. And I have formula for the left-hand side because I can use the same formula here. And this is equal to n plus 1 choose 3. Yes? So I have formula for this one, and I have formula for this one. And so I can find formula for the sum of squares. Okay?
N plus 1 choose 3, right?
N plus 1 choose 3, yeah. K we have 2, k equal to 2, and m is equal to n. No. Here I have m equal to n minus k. Because here I write k plus m. So in our formulas, I can. So usually here we will have an n here, and so we will have an n plus 1 here. So k will be different. K will be 1, 2, 3, and 4. But k plus m will be equal to n, and so k plus m plus 1 will be n plus 1 always. Okay? Okay, so let's do the calculation. Here. So if I want to find the sum of squares, yeah?
Hello.
Hello?
I have a question. Should we choose 3 choose 2 plus n choose 2
Yes.
is equal to n plus 1 choose 3?
Yes,
All of them or only some parts?
all of them. So this, I just use the identity that I prove on the other board. That so all the sum
Oh,
is equal to n plus 1 choose 3. Okay. So I need multiply it. So this will be 2 times n plus 1 choose 3 plus. So I maybe I did a mistake. I did so I move 1 plus etc plus n to the left hand side and multiply all parts by 2, all sizes by 2. So for this we have formula n times n plus 1 over 2. And n plus 1 choose 3 is by the formula n plus 1 factorial divided by n minus 2 factorial times 3 factorial.
Sorry, the first coefficient should be 1 or 2 instead of 3.
Here?
Yes. It's not 1 or 2?
Yeah, because I have 1 over 2 here, so I multiply it all by 2, all two parts. And so here will be 2 times n plus 1 choose 3.
Oh.
Okay. So here I can rewrite this as n plus 1 times n minus 1 over 3 times 2 times 1. And so I can cancel 2 here. And I need to calculate this plus n times n plus 1 over 2. So of course I can take n plus 1 outside the brackets, and inside I will have n minus 1 divided by 3 plus 1 divided by 2. And here I need to calculate this. This will be 2n minus 1 plus 3 over 6. And this is 2n plus 1 over 6. So finally, I will have 1 squared plus 2 squared plus n squared equal to n times n plus 1 times 2n plus 1 divided by 6. So we can check this formula. Maybe, for example, we choose, I don't know, n equal to 3. So this will be 1 squared plus 2 squared plus 3 squared is equal to 1 plus 4 plus 9, 14. And here I'll have 3 times 4 times 7 over 6. And so this is 2 times 7, 14, okay? So for n equals 3, this holds. Questions? Okay. So the same holds for the all other sum of powers. I cannot write the explicit formula for these powers, but I can provide an algorithm to find all these sums using the results for the previous. So for example, if I want to find the sum of the cubes, I want to know the sum of the first powers and second powers. And knowing this, I can write formula which after the calculation will be a formula for the cubes. So we can try to do the same for the cubes. So how can we find it? We use this identity for the k equal to 3. I can write it here, so I can take 3 choose 3 plus 4 choose 3 plus etc. plus n choose 3 is equal to n plus 1 choose 4. And then I can rewrite all the binomial coefficients in the left-hand side in terms of cubes, squares, and just numbers. So if I look at what is k choose 3, it is k times k minus 1 times k minus 2 divided by 6. And so this will be k cube minus 3k squared plus 2k over 6. Because I will have, so k minus 1 times k minus 2 is k squared minus 3k plus 2. And so this will be multiplied by k here. And again, as in previous calculation, I can first of all, I can write here, I can write the sum from the 1, not from the 3, because if I 1 choose 3 will be by this formula 1 times 0 times minus 1 over 6, 0. And 2 choose 3 will be 2 times 1 times 0 over 6, 0. So I can write something like the following. So 1 over 6, sum of the cubes, minus 3 times of sum of squares, plus 2 sum of the first powers, equal to n plus 1 choose 4, which is n plus 1 times n minus 1 times n minus 2 over 24. So here we can do some simplification. We can write this 4 instead of 24. We can use the formula for these guys. So sum of cubes is 3, the sum of squares, which is n plus 1 to n plus 1 over 6, minus 2 sum of 1s, which is n plus 1 over 2, and plus n plus 1 times n minus 1 times n minus 2 over 4. So I just need to do this simplification of this formula. This will be polynomial of n of degree 4. We can see that we will have n plus 1 everywhere, so we can just take it outside the brackets, and then just calculate what is left here. So I have the sum of cubes is equal to n times n plus 1, brackets open, 2n plus 1 over 2 minus 1 and plus n minus 1, n minus 2 over 4. So I can multiply it all by 4. This will be 4n plus 2 minus 4 plus n squared minus 3n plus 2. And here we'll have these terms cancel. And here I'll have n squared plus n. So totally it will be n plus 1 squared divided by 4. Let's again check it for some arbitrary n. So for example, I have n equal to 3. Oh, sorry, I count cubes, not first power. One plus 8 plus 27. This is 36. And here I have 3 times 4 squared divided by 4, which is 9 times 4, which is also 36. Okay. So for n equal to 3, this formula actually holds. So we can continue and find the formula, for example, for fourth power, for fifth power, and so on. It will be the polynomial of n, the degree of power plus 1. So here we'll have polynomial of degree 4. Here we'll have polynomial of degree 3 when we calculate the sum of the squares. Here we have polynomial of degree 2 if we just take the sum of first powers of n natural numbers. Okay, any questions? Okay, let's continue to the next concept. Maybe you're familiar with it. I don't know if you're familiar with it from the first part of the course. But of course, if we talk about the generalization of binomial coefficient, then we can ask about if we talk about binomial coefficients, we talk only about two types of elements. For example, if you count in subsets of an element set, then we just divide it in two parts: the elements with the elements which are we choosing and the elements which we're not choosing. But sometimes we need the more types of these elements. So, for example, we have some words. For example, mathematics. And we want to count how many different permutations we can make from this word. So I want to permutate the letters. So how many different words I can achieve if I just will be how many words by the letters of this word. Do you know how to solve it? What is the answer? So, for example, I can just take so I can have this word, I can just write and permutate it in every possible way. So the all possible permutations will be 11 factorial.
Just for A, P, there is two of them.
So if all elements if all elements were distinct, then we will have an 11 factorial as all kind of type of permutations. But he will have two m's, two a's, and two t's. And all other letters will be occurring only once. So what I need to change in the formula of 11 factorial to get all this permutation? Why do you divide by 3 factorial? So let me maybe simplify this a little bit. For example, if we have only two letters A and B, and we want to look at the word with, for example, two A's and three B's. So how many words do you think we can get from two A's and three B's? Yeah, for example, here, if you have 2 A's and 3 B's, then we have, I suppose, 10 different words. Yeah? 5 factorial of 5 will be 120 over 5, and it will be 24. And here I'll have only 10. So, yeah. Yeah. 2 factorial times 3 factorial. Why 2 factorial and 3 factorial?
The order letters, like these 2 B's, and you also have the same thing, but with the 2 B's with that. But since they're the same letter, should we exclude these?
Yeah, of course. So the idea is that, for example, if I have one green A and one red A, so they will be distinct. Then, and all the B's will be different types of colors. Then I'll have a 5 factorial. But now I have, for each of these words, I have 2 possible choices. I can, for example, if I look at the word A, B, 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 then I can take the first letter will be green, the second is red, or otherwise the first will be red and the second will be green. So I have 2 possible ways of choosing the colors. And for the 3 B's, I have 6 possible 3 factorial ways of choosing the colors of these 3 letters. And another way of saying this is just binomial coefficient. If you look at this formula, it's just 5 over 2, 5 choose 2. This is because here I have 5 element set, so I just choose the positions of letters A. Yes, so I just choose, for example, A will be, if I choose the subset of 1, 3 from the 1, 2, 3, 4, 5, then I will put letters A on one first position and third position, and other places I will be choosing for the letter B. And so this is the concept of concept of binomial coefficients is nothing but the, how many words can you get if you have only 2 letters. Okay, but what if I have more types of elements? So here I have many different types of elements. I have M, A, T's, E, H, C, and S, and I. So I have like eight types of elements. So how do I change this formula? So what I should write here? Do you understand now? So it will be 11 factorial divided by, yeah, just write just the number of how many times each letter occurs in this word. So I have like 11 factorial over 2 factorial, 2 factorial, 2 factorial, and then 5 times of 1 factorial. And this is the concept of so-called multinomial coefficient. Okay. Доска сохраняется где-то. Доска сохраняется как файл. Нет, это я понимаю, да. Ну ладно. Окей. So, if I have n element set, and I want to choose n1 elements of type 1 and 2 elements of type 2 and so on, nk elements of type k, such that this I have count all the elements, so the sum of the n1 plus n2 plus etc. plus nk is equal to n. Then the number of ways of choosing these elements is called multinomial coefficient. Multinomial coefficient. We can denote it by m of n1, n2, etc., nk. So if k is equal to 2, it is a binomial coefficient, and if so if k equal to 2, this is just binomial coefficient, and in the arbitrary case, this is multinomial coefficient, and we can prove that the formula that m of n1, n2, etc., nk is n1 plus theta plus nk factorial divided by n1 factorial, n2 factorial, etc., nk factorial. So I think you already understood the proof, but if I need to I need to give a correct proof. I just can say that we have an element set, and if we choose n1 elements of type 1, so we have like n positions. And if I choose n1 elements of type 1, this means that I need to choose the n1 element subset from this n element set. So choosing the elements of type 1, choosing of type 1 is the same as choosing n1 element subset in my set. And we know that the number of n1 subsets in my set is nothing but n choose n1. And so if I choose the elements of type 1, then I need to choose from elements that are left, so n minus 1 elements, the elements of type 2. So now I want to choose n2 elements of type 2. And I need to choose them from the n minus 1 element set. And so this can be this I can do is in exactly the n minus n1 choose and two possible ways. And then I need to choose elements of type 3. This I need to choose it from the set consisting of n minus 1 minus n2 elements. I need to choose n3 elements, and so on. So if I can calculate this, so I just now expand. So I just use the formula for the binomial coefficients, and then after calculation, I will get this formula. So I'll have n choose n1 times n minus n1 choose n2 times n minus n1 minus n2 choose n3, and so on. And those, the last one will be n minus 1 minus 2, etc. minus n minus k minus 1 choose nk. And so if I write this in terms of factorials, this will be n factorial divided by n1 factorial time n minus n1 factorial. The second one will be n minus n1 factorial divided by n2 factorial n minus n1 minus n2 factorial. The next one will be n minus n1 minus n2 factorial divided by n3 factorial right n minus n1 minus n2 minus n3 factorial, and so on. And the last one will be the n minus n1 minus n2 minus etc. minus n minus k factorial, but we know that this is equal to nk because sum of this n's is equal to n. So he will have nk factorial and 0 factorial. Okay, so he will have some cancellations. We can see that he will have n minus 1 factorial, n minus 1 factorial, n minus 1 and minus 2 factorial, he n minus 1 minus 2 factorial, and so on. So the final formula will be n factorial over n1 factorial, n2 factorial, etc. and k factorial. Zero factorial. So 0 factorial is 1, and n factorial is n1 plus etc. plus nk factorial. So we have the formula that we stated there. We prove the proposition. Suppose we have 15 students and we want to divide them into 4 groups in containing 4 students each. So the first question, how many possible ways of doing this if groups are distinguishable, and the second question, what is their non-distinct. So in the first question, you can assume that we have, for example, groups A, B, C, D, and we want some 4 of the 16 students go into the group A, some 4 into group B, some 4 into group C, and some 4 into group D. And for the second one, we just want to separate them into four groups of 4 students. What distinct? Non-distinct means that we just want to just make the 4 so these groups are indistinguishable. So for example, if we can make this partition. I just enumerate all the students. So we have 4 groups. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13, 14, 15, 16. And so it doesn't matter if this. What doesn't matter is that the students is in one group. It doesn't matter in which order we how we order these groups. So for example, here we can make that this this way of distribution is not the same if we name this group B or this group A. Yes, so this is different types of distributions of students. But in the second part, we care only about separating the students. If your denotation like 16, 4 is 16 choose 4, then I think your answer is not correct.
For the second one?
No, I answer Vahid because Vahid sent me answer by private message here. So you can just check your answer, because if you for example, if you have 4 students, then for the second part, we have only one possible ways of form 4 groups, because each student is forming one group. Yeah. And for the first, we just want to choose 1 student for A, 1 student for B, 1 student for C, and 1 student for D. And how many ways of doing this? It's all permutation, so it will be 4 factorial here. So if we have 4 students, then for the first one will be 4 factorial, and the second will be 1. And Vahid sent me an answer in which he. So, 16 factorial?
Over 4 factorial. 16 factorial over 4 factorial.
Why?
The first one is also incorrect.
Yeah, of course, because you need, if you have 4, then we'll have a factorial, and your answer is not for factorial. Your answer is much more than for factorial in the first one. And for the second one, I think it's correct, yeah. Because you made the same mistake for the first and the second. So if you correct the second, you need to also correct the first one. Okay, so. Multiplied, because he will tell that you will need to divide, but not multiply it.
Second? No?
No.
Okay.
It's similar to, because if you take for students, then your answer will be, for the second one will be this one, which is for factorial, but we have here one.
Why?
Because we have for students, you want to divide them into 4 groups consisting, each consisting of 1 student. It is just, we have only one possible way of doing this, just taking each student in this group and so on. And that's all. How can you, another, you don't have another way of taking 1 student in 1 group. You can just separate them on this way. Each group are indistinct. So, for example, yes. Yes.
So if we change them, we change, for example, exactly. We have another presentation. This is why
Yeah, but nothing changed because this group are, if they're distinct, we can write the letters here. And of course, if you choose the letters, the places of the letters, then we change the way of ways of separating the students. But if they're indistinguishable, then if you change A and B, that nothing changes. It will be the same distribution. Because, for example, assume that we want to, I don't know, provide a championship in some game where in team we have only 4 persons, yes? So we want to provide some tournament. So all we need to do is make 4 teams of 4 students. It doesn't matter. So what doesn't matter is which students are in which team. It doesn't matter how the team are named. I want just divide them into 4 teams of 4 people. So all I need, for example, here I want to separate them and make, so there will be 1 person. In each team will be only 1 person, so I have only 1 distribution. Is just take each person form each own team. So it will be only 1 possible way of doing this. Yeah, I think now your answer is correct. Yeah. So, okay, maybe I should start with some simple examples. So, for example, we have 10 students, and we want to organize a basketball match. And in the basketball match, only 5 persons are participating. So I want to divide them into 2 groups of 5 students. And so how many matches can I provide if I need to divide these 10 students into two groups of 5 students? So I need to choose 5 students on the first team, and so yeah, it will be 10 choose 5. But I need to remember that I can choose the 5 students on the first team, or I can choose, so if I have 10 students, then choosing, for example, this guys in the first team is the same as choosing the opposite members in the first team. Yeah, so I need to. So for example, here I can have 1, 4, 6, 8, 9 here, and 2, 3, 5, 7, 10 here, or I can have 2, 3, 5, 7, 10 here, and 1, 4, 6, 8, 9 here. And this is the same match, the same game, because the same members of the teams. But I just change the teams, the place of the teams. So I count. So if I take this as an answer, then I count all possible situations twice. So I need to. Yeah. So I need just divide this by 2. Yeah. And same idea is working for this exercise.
Those are tendencies, the same as how many words you can make with the letters of another word.
Just sorry, could you repeat, because I fully.
I wanted to say, is this question the same as the question we solved before in mathematics? When we have repetition in letters, we have to divide the numbers of repetitions. For example, the class groups are the same. We have 4 same groups, so we have to divide it by combinatorial. And in the word question that we have to make words with mathematics letters, we have to divide it by the letters which were the same.
Yeah. So yes, the first part of this exercise is the same as multinomial coefficient, because I want to. Yeah, you're right. But the second is a little bit more complex than just the multinomial coefficient, because here I need to, as in this example, I need to divide this over some new coefficient. So I need to divide this over 2. So I can provide an example about letters. So for example, this one, it means that we have 10 positions. And we have 2 letters, team A and team B, but we didn't care about, so we can change A and B places between A and B, and this will be the same word. So A, B is equal to, because I don't care about which letters are A and which letters are B. All I need to do is that this will be the distinguished from this one, or this one distinguished from this one. And so this is not just the number of words. I need to divide it over 2, because I have this symmetry. I have these repetitions because I have new identity between the words. I know how to say it, because it's not much. It's not a good example here. Yeah. So what about it? Can you get answers to 1? Yes. Yeah, so the answer for the first one is just the multinomial coefficients of 4, 4, 4, and 4. Because here I have just the definition of multinomial coefficient. I have 16 students, and I want them divided into 4 groups, and each groups are so the 4 elements of type A, 4 elements of type B, 4 elements of type C, and 4 elements of type D. And this is just exactly the multinomial coefficients of M of 4, 4, 4, 4, which is 16 factorial over 4 factorial to the 4th power. Sorry? Could you repeat? Yes? Yeah, so and the second one is the same, but now for each, here I just need to divide overall permutations of this A, B, C, D. So if in the first task I have 4 different groups, A, B, C, and D, then in the second I make them indistinguishable. So I forget about the order of these groups. And so, for example, if I have this distribution, then I can imagine that I have all possible ways of choosing the letters for these groups. And they're exactly 4 factorial for them. So for the 2 will be 1 over 4 factorial of M of 4, 4, 4, and 4. Of 16 factorial over 4 factorial to the 5th power. Exactly the same way as I have here 1 over 2. This is 1 over 2 factorial because I cannot distinguish these 2 teams here and teams here. And here I have this additional coefficient. Okay? Okay. A little bit. Okay. Maybe I will give one more example to check that you all understand the idea. So what if we change a little bit our example, and we have 16 students, but now we want to make 3 groups of 4 students and 2 groups of 2 students. So totally will be 12 and 4, 16. And again, the first question, what if these groups are all distinct? And okay, and the second one, what if they're indistinguishable in terms of that? So the groups consisting the same number of students are indistinguishable. So of course, if we can distinguish the groups of 4 students and group of 2 students. But what if groups of 4 students? So these 3 groups of 4 students are indistinguishable between each other, and these 2 groups of 2 students are indistinguishable with each other. If the groups consisting the same number of students are in this like he sent me the following answer for the first one, but I think it's not correct. He wrote M4, 4, 4 times M2, 2. I don't think this is correct because here you divided the 12 persons into 3 groups of 4, and here you divided 4 persons into 2 groups of 2, but you also need to choose the 12 persons to go here and 4 persons to go here. And so there will be, we don't take the first 12 students to the 3 groups, we want to permutate them, so these 3 groups can be considering all types of 4 students. So I don't think, I think this is not correct. You need to sorry? Yeah, just a click, because here you do the following. You just take the first 12 students and put them into 3 groups of 4, and you take other 4 students and divide them into 2 groups of 2. But I can take another 12 students here. So for each 12 students, I have the same number of distributions. So, for example, if I have one group of 3 students and one group of 2 students, then your answer will be m of 3 times m of 2, which is equal to 1. But it's not, I can, actually I can get many different types of groups. If I have 5 students, I want to have one group of 3 and one group of 2. Yeah? Yeah? Answer? Answer? Is the first one or the second one?
First one, I think.
First one?
Yes.
No.
No?
No.
See?
Why you divide this over these 2 guys?
Those.
Yeah. Why you divide it over? So what's? Oh, excuse me. What's a 3 on 3? 3 factorial?
Yes.
Why divide it over 3 factorial here?
What if this answer is for the second one? It's still not reasonable? Still wrong?
For the second one, this is reasonable, but for the first one, no.
So for the second one is correct.
Yes, yeah, because
Yeah, I forgot.
the same. We have the same idea here and here. So for the first one, all we need to do is just we have 5 labels. For example, A, B, C, D, E. We have 5 labels in terms of groups, and we need to choose. So we have 4 A's, 4 B's, 4 C's, 2 D's, and 2 E's. So 2 elements of type D and 2 elements of type E. So how many possible ways of have? So we have 16 elements, and we want to have 4 elements of type A, 4 elements of type B, 4 elements of type C, 2 elements of type D, and 2 elements of type E. How many possible ways of doing this? Yeah, we can just use the same definition of multinomial coefficient here. It will be just, so for the first one will be m of 4, 4, 4, 2, and 2. The same idea. As here is not differ much, because why am I bothered about how many elements are in my groups? Here I have 4 groups of 4 elements. This have 3 groups of 4 elements and 2 groups of 2 elements. The answer is the same. But if you want to write a formula, it will be 16 factorial over 4 factorial cubed and 2 factorial squared. But the idea is the same. Yeah, okay. Or maybe you have some questions? Yeah. Yes, Wahid?
Yes. Is it possible to construct a correct solution, correct answer with one solution?
Yeah, if you have, so what you do, is you already divide them into group of 12 and 4, and then divided them into 3 groups of 4 and 2 groups of 2. So if you want to have the correct answer, you just need to multiply it by 16 choose 12, because you firstly you just choose 12 persons from the 16, and then divided these 12 persons into 3 groups of 4, and then divided the 4 persons into 2 groups of 2. Because so here you have like this multiplication, and so if I multiply it by 16 choose 12, I will have the same formula that I have when I proved the multinomial formula. The proposition for the multinomial formula will be 16 choose 12, 12 choose 4, 8 choose 4, and 4 choose 2. It is the same as this one. So, and for the second one, some of you just already show me the correct answer. I need to do the same idea. So if I have these groups are indistinguishable, that I need to divide it by the multiplicator of all possible permutations. So for the second one, I just need to take M44422 and divided this by 2 factorials for permutations of these 2 groups, and 3 factorials for the permutation of these 3 groups. Because now I can, so I can't forget about D and E. You don't see this?
I don't see that. Yeah, that's my way. That's why for me it's more understandable.
Okay.
Go on, sorry. I'm fine.
So if I made them indistinguishable, that I can't forget about the permutation of D and E, so I will count them twice. And for these 3 groups, I count them six times because I have ABC, BCA, CBA, etc. 6 possible permutations of these 3 groups. So I need to divide them over 3 factorial and 2 factorial. So this will be the correct answer for the second task. Any questions? Okay, so let's continue. I think I will now prove the generalization of binomial theorem, and then we'll have, I don't know if you need to, maybe I will give you one more task and then we'll finish for today. But maybe we can make a break if you are very tired. So again, we proved already the binomial theorem. Binomial theorem, which is, so if I want to expand a plus b to the nth power, I need to write here the binomial coefficients. The same holds if I want to express the so I want to expand the not 2 but several different terms here. So what if I have here x1 plus x2 plus etc. plus xk to the nth power? Again, I will have some in which I have all possible monomials consisting these variables. So here I have x1 to the power g1, x2 to the power g2, etc., xk to the power gk. And such that g1 plus g2 plus etc. plus gk is equal to n. So I just, if I so I have like n brackets. I can imagine that I have n brackets, and from each bracket I choose one variable. So from this I can take x2, from this I can take x3, from this I can take also x3, and so on. So I have n brackets, and if I choose from each bracket one variable, then this forms this monomial x1 to the j1, x2 to the j2, xk to the jk. And the question is, what I should write here? So what is the coefficient for this term? So if I have k equal to 2, then I have binomial theorem, and he will have binomial coefficient. But if we have k different variables, then we have here multinomial coefficient. And so the answer is m of g1, g2, etc., jk. The coefficient will be multinomial coefficient of this g1, g2, jk. And this is called, similarly to binomial theorem, this is called multinomial theorem. Multinomial theorem. So if you need an explicit example, again, similarly to the properties of binomial coefficient, if I look at the sum of all multinomial coefficient, sum of multinomial coefficients with the constant sum, which means that I actually want to calculate the all possible distribution of n element set I want to have all possible distributions in the k types of elements. I don't know. So maybe I want to have one element of first type, two elements of second type, and so on. Maybe I want to have two elements of the first type, two elements of second type, and so on. It doesn't matter. I want to calculate all possible distributions into k type of elements. And how? So how much of these distributions are? So for example, I have, I don't know, 3 element set. or it will be too much. Okay, and three types of elements. It means that I have like letters A, B, C, and I want to calculate all possible words consisting of 3 letters, 3 element set, and of elements A, B, C. So I can have word AAA. It means that I have 3 elements of type A and 0 of type B and C. Or I can have like BBC. It means that I have 0 elements of type A, 2 elements of type B, 1 element of type C, and all possible words which I can make of 3 letters. This words consisting of 3 letters and type of letters in ABC. So how many possible words I can? No, it's 3 factorial. It's just the permutations of ABC, but yeah, it's the same as the arrangement with repetitions. Yes, arrangement with repetitions, because I care about the places. But here I can put so on the first place I can have every letter A, B, and C. On the second place I can have every element A, B, and C, and on the third place I can have all 3 elements. So this will be just arrangements with repetitions, which is 3 to the 3 power. And here I will have like I will write the 2 answers, and you tell me which is true. This one or this one. So if I have n element set and I have k types of element, how many possible arrangements can I have? I think we will meet. So we will be voting for this one and this one, and we will discuss. So the answer will be taken by the majority of votes. Yeah. No. Who thinks this is the first one? The first one? The second one? Second one. Okay. And the others? What do you think? This is. So again, I have k letters, and I want to think about how many possible words of length n I can construct using k. So I have k letters in my alphabet, and I want to think about how many words of length n can I write. This will, so what will be n to the power k or k to the power n? Yeah, of course, because if I have n places, then the first places can be chosen one of the k possible variation, the second place can be chosen one of the k possible variations, and so on. So I need to multiply it, and after multiplication, I will have k to the power n. So I can write that this sum of multinomial coefficients is nothing but all distributions of an element set into k type of elements, and this will be k to the power n. And this reminds you of binomial theorem, because if we have only 2 types of elements, this is nothing but the sum of binomial coefficients. And this is 2 to the power n. And so this formula correct for the k equal to. Because this will already prove that by binomial theorem, this will be to the power n, and this is exactly one of the proofs why this identity holds. Okay, so we can prove it just using the formula on the left board by taking. So if I take x1 equal to 1, x2 equal to 1, etc., xk equal to 1, then I will have, on the right-hand side, I will have the sum of all multinomial coefficients with the sum equal to n. And on the left-hand side, I will have 1 plus 1, etc., plus 1 to the n power. So this will be exactly k to the power n. So trivial. So from this formula we can trivially get the sum of all multinomial coefficients, for example. Okay, how to prove this theorem? So actually, all I need to prove is that how do we get this multinomial coefficient? Again, we want to take as these coefficients before this monomial as some choices. So I have like some n element set from which I choose the G1 elements of type 1, G2 elements of type 2, and so on. And all I need to do, as in binomial theorem, I can just look at these n brackets and just think. So I need to choose. So if I want to achieve x1 to the j1's power, I need to somehow choose the brackets from which I choose x1. Yes. So I need from these n brackets, I need to choose exactly j1 brackets from which I choose x1. And I need to choose g2 brackets from which I choose x2. So for example, here so I choose x1 from these brackets, choose x2 from these brackets, and so on. And so all possible ways of choosing, so all possible ways of achieving this monomial into this type of brackets is exactly possible ways of choosing J1 brackets for variable x1, choosing J2 brackets for x2, G3 brackets for x3, and so on. And this is exactly the number of ways of choosing J1 brackets for x1, J2 brackets for x2, and so on is exactly the definition of multinomial coefficient. So this will be m of J1, J2, etc., Jk. Okay, any questions? Yeah, I want to give you 2 more exercises, but I don't know if you want to. It will break like 5 minutes, so you can make it, but maybe we will. So I don't think that will take. So we'll have two exercises, I think, for 20 minutes, and that's all for today. So I think we can do it without break, but if you want, we can make a break 5 minutes. Okay, so okay, first task will be So suppose we have this expression, x to the power 2 plus x to the power 5 plus x to the power 7, all this to the power of 20. And I want you to calculate okay, so for example, I don't know, what is the coefficient will be before x to the 37 power and x to the 38 power. So if we expand this, then what should be coefficient to this guy and to this guy? Again, I have, so maybe I write the not very not a very simple example, but here what simplification can we do? First of all, we can get rid of the x squared because all these three guys divided by x squared, so I can write something like 1 plus x to power 3, x to power 5 to the 20, and here I need to find coefficients for terms like 17 and 18, yes? No? Because this divided by squared, this divided by squared, this divided by squared. So I can, if I can get rid of x to the power 40, yes? Here. So all I need to do is to find this expression. So all the question, so the question here will be how many possible ways of getting 57 into the sum of 2, 5, and 7 if we have exactly 12 summers. And here's the same. So I want to describe 17. So I want to describe 17 in terms of, so if I look at, so I want to denote this like A, this will be B, and this will be C. So if I expand A plus B plus C to the 20th power, then we will have like some monomials like A to the power G, B to the power I, and K to the and C to the power K, where J plus T plus K is equal to 20. So this will be the same way. So this will we have. So if I expand these guys, then I will have 1 to the power G, x cubed to the power I, and x5 to the power K. And I want to find all possible ways when this is equal to x to the 17th power. Yes? This is just multinomial theorem, but here's a little bit complex because maybe I will have several possible ways of doing this. I think for 17, there's not. What is the possible ways of 17? I want to describe 17 as sum of 5 and 3. Yeah? Sorry. Yes, so 17, for example, can be described as 5 plus 3 plus 3 plus 3 plus 3. And I think it's the unique possible way of describing 17 as sum of 5s and 3s, yes? So here I'll have I equal to 4, K equal to 1, and J is equal to 15. Okay, so now I can write the answer. So what's the answer?
What?
Because I have 20 possible total brackets will 20, but it doesn't matter here because so all other elements I will take it from this one. So here I need to take, so if I look at the first expression, that I need to write something like x squared to the 15th power times x to the 5th power to the 4th power and x to the 7th power first power. So this will be x to the 30th, x to the 20th, and x to the 7 will be exactly x57. Okay, so what is the answer to the first? Yeah, of course. So if in short way, I just need to write this m of 15 for 1 here. Okay. Sorry. So for the x17, the answer is multinomial coefficient of 15, 4, and 1, or in terms of factorials, it will be 20 factorials divided by 15 factorial, 4 factorial, and 1 factorial. Okay, here we have two different answers. This one and... Okay, so this one or this one?
No. You see, e can be 6, like x to the power 3. Your e
Yeah,
can be 6,
yeah.
and k.
I think it's saying 1631.
Okay, yeah, I can give you 2 more minutes and then we will
Just here we can express in 2 ways.
yeah, but if you can express in 2 ways, then what should be answer? So what will be answer? What will be the answer? Yeah, of course. So if you have 2 ways of doing this, that of course we need just to summarize it. Take the sum of it. So for 18, we can have only using only 3, or using 3, 5, and 1, 3. So it's maybe more precisely to write this not 3, 1, but 1, 3, because we write here, we usually write the number of 3's in the second place and number of 5's in the third place. So if you have more possible so if you want to write answer for the arbitrary power of x, you just need to summarize all possible variations of describing this power in terms of these summands. And so the answer will be the sum of these m's, of this multinomial coefficient. Okay? And for the last one, okay, again. Okay, so if I want to get x to the power 18, I can get either 6 times 3 or 3 times 5 and 1 times 3. So I want to so if I want to expand this guy, I need to look at the coefficients when we have 1 to the power 16, x cubed to the power 1, and x5 to the power 3, and the coefficients of x3 to the power 6, x5 to the power 0, and 1 to the power 14. This will be, and this also will be equal to x to the power 18. So as the answer, I need to take the sum of it. So that the answer will be m of 1460 plus m of 16, 1, 3. Okay. And the last exercise. Find the following sum. What I want to find the sum of I plus j plus k equal to 5, m of I j k minus 1 to the power I plus j. I take the sum of all possible ways. Of course, this indexes must be line between 0 and 5 natural indexes. Can I find this expression? Again, all you need to know is the multinomial theorem and nothing else.
Zero?
0?
Yes.
Not quite 0, similar to 0, but not 0, I suppose. You may be right, because this is maybe remind you of in the first lecture we were discussing the alternating sum of binomial coefficients, and so we know that if we look at the alternating sum of binomial coefficients, it will be 0 for n greater than 0 and 1 if n equal to 0. And so if I can write this in terms of multinomial coefficient, then this will be sum of I plus j equal to n, m of ij minus 1 to the i's power. So this is the same, yes? Because m of ij is nothing but the binomial coefficient, and minus 1 to the power I is just the alternating sum. So this is the generalization of this sum somehow to the different different numbers of variables here. So not binomial, but multinomial alternating sum. And of course, we can find this guy using the ideas for this identity. Yes, exactly. So all we need to do is just to write here 1 to the k power, because it doesn't change anything, yes? And after that, just looking at the multinomial theorem and try to imagine what I can take by x1, x2, and x3, such that this formula will be represented this formula, yes? So what are variables? What variables I need to choose such that multinomial theorem will be written as this one. First question is how many variables here in my multinomial theorem? 3. Okay. So what I take is x1, x2, and x3. X1 is 1, x1 is 1 is 1, x2 is minus 1, and x3 is 1, yes? So instead of question, I need to write minus 1 plus 1 to the 5th power. Yes? And this will be minus 1 to the 5th power minus 1. Just using the multinomial theorem, we can calculate this whole sum into one simple expression. Okay? Yeah, of course. I want to. So this is just. I can write this maybe more So I can write it as m I j k minus 1 to the power I minus 1 to the power j and 1 to the power k. And this one is just the multinomial theorem, but when I can get x1 as minus 1, x2 is minus 1, and x3 is 1. If this is the same, I can write this as sum of I plus j plus k m of ijk is x1 to the I power, x2 to the j power, and x3 to the k power, where x1 is minus 1, x2 is minus 1, x3 is 1. And this is nothing but x1 plus x2 plus x3 to the k's power. And here I have so I just need, again, it is the same as binomial theorem. So in binomial theorem, he said that this is just 1 minus 1 to the nth power, and so this is just equal to 0 when n is greater than 0. And the idea is the same. You just use the binomial theorem and just take one of this is 1, one of this is minus 1, and if you expand it, you will get the alternating sum of binomial coefficients. This is the same. This is some alternating sum of multinomial coefficients. It's just nothing but multinomial theorem for some numbers. Of course, I can do this different task here. So, for example, I can find the sum. For example, I, j, k, I plus j plus k equal to 10. When I have 1 to I, 2 to the j, 3 to the k, for example. So I can use the arbitrary numbers here. And of course, I can do a little bit tricks here and just forget about I, for example. And you think this is just some different, but not, it's very easy, but you just can add 1 and you will get the again, it will be just multinomial theorem, so I will just need to write 1 plus 2 plus 3 to the 10th power. Okay. I think this is maybe more or less all for today, but I want to ask you about what you have completed in the first part of the course. So, do you familiar with inclusion-exclusion formula? Do you prove this? Do you need to? Yes. In exclusion. So I don't need to prove it. Okay. Yes. Yes. Inclusion formula. Okay. And do you calculate the number of derangements? Derangements. No? It's just so you have, for example, you have an element and you want to calculate all the permutations where none of this element is standing on its own way, on its own place. So for example, for 1, 2, 3, I restrict, so 1 should not take the first place, 2 not be taking the second place, and 3 not be taking the 3rd place. Yeah. Okay, so I need to remind you how do you calculate it. Yeah. Okay, and the last question: do you talk anything about recurrence relations? Recurrence? No. For example, Fibonacci numbers. Do you get formula for the Fibonacci numbers or no?
In the first semester.
Okay, and do you know? So
Long time ago.
yeah, but Okay, but you know, don't know anything about other linear reconciliations, yes? Yeah. Do you prove the theorem? So, for example, you have a sequence of A1, A2, etc., and you know that AN is alpha AN minus 1 plus beta AN minus 2. So how do you find the formula for the AN? So Fibonacci numbers is the one of the examples because you have this recurrence relation. But I want to talk about this. So you don't know about this. Okay. Okay. So I think this will be the main for the next lecture. This will be the main topics. So usually in combinatorics we have not much formulas, explicit formulas for finding. So here we have good luck because we can find the formulas for multinomial and binomial coefficients. But in arbitrary situation, sometimes we can just try to express some formula of n in terms of formulas on previous elements. And so in so if these relations are good ones, we can find the explicit formula. But sometimes it's complicated. So one more question. And do you discuss Catalan numbers? No?
What number?
Catalan? No? Catalan numbers. Okay. So we will have. So I will start reminding you of inclusion-exclusion formula, and then we will discuss some different relations and can we find the formula for these relations in this linear dependencies, or maybe some more complex dependencies. Okay, I think that's all for today.